Hey, Physics 30s, it's Mr. Jukely again. We are right in the middle of Unit 6, I guess. Lesson 3, we're talking about half-life today. And in doing so, we're going to talk about radioactivity and a couple other things as well. So, as we go through, first and foremost, measuring radioactivity. Well, radioactivity is the rate at which we have radioactive emissions. And remember, we talked about before, radioactive emissions come from radioactive decay. We've got alpha, beta, that's beta positive and negative, and also gamma. In other words, it's the number of emissions per unit time. So the very common, and there's loads of different units for this, but the common unit that we are going to use in our class is becquerels, BQ, where 1 becquerel is equal to 1 emission per second. This is after Henry Becquerel, so there's a picture of Henry Becquerel right there. Henry Becquerel, I thought I had something else on him on here, but I guess not. Maybe that was one of the previous lessons. I'm kind of losing it here. I'm not going to lie. Henry Becquerel accidentally discovered the idea of radioactivity. I think I did actually talk about that from before, so we'll leave it there. Anyways, radioactivity is measured using a Geiger counter. So, you know, when you see the people in their suits. Oh boy, I don't know why I started drawing this suit. Okay. Yeah, and then there's the little device. Okay, we're going to stop drawing that right now. People in their little like yellow hazmat suits, and they walk around with a little thing and it clicks or beeps. That's the Geiger counter for radioactive materials. So essentially what happens is we have that ionizing radiation. So remember, alpha, beta, or gamma radiation comes in. It strikes one of the atoms, turns it into an ion. The free electron goes and hits an anode, which sends some potential difference or some current over, and then it counts how many of those electrons actually come in, which is kind of neat. Things that we've got when we're talking about this radiation, we've actually got a ton of natural background radiation. So our body is constantly bombarded with small doses of radiation, which, you know, when you think about that, radiation typically not thought of with you know, in the same sentence as, you know, healthy lifestyle. But we've got it from our occupations, from medicine, from the fuel cycle, from consumer products, from environment, from natural background, all kinds of different things. Some of it just even comes from the earth, right? So we got uranium deposits in the earth. The uranium deposits are giving off radiation. They're creating radioactive material around it. And if you've got a big fireplace in your house, chances are some of those bricks have very, very small amounts of radioactive material, giving off very small amounts of decay, right? Of radiation. Other places, well, cosmic radiation, and honestly, I forget which video I watched, but there's a video, I believe it was on Netflix, and the opening line was, "The sun is constantly trying to kill us." Um, so, I mean, there's a big stream of this ionizing radiation, protons, electrons, other things that are coming from the sun, very, very, very high energy particles coming from the sun. And realistically, those high energy, those ionizing would kill us, and the Earth would be a very, very different place. But lucky for us, we're protected by this radiation by our atmosphere and our magnetic field, which is excellent. And we talked about that in Unit 3. However, when you go really, really, really high up, Earth and its people, well, they receive more of this radiation and need to be protected from it. So you see astronauts with the gold film over their helmets, and airplanes, they're protected from it as well. Okay, so this radiation and radioactivity, people are curious about it, obviously, and these different materials that can do different things. Marie Curie, now Marie Curie is, I like Marie Curie. She's an interesting lady. She's done a lot in her lifetime, or did a lot in her lifetime, I should say. I'm just going to take a moment to talk about Marie Curie because we have talked about, let's see, 0 female scientists so far in physics, which is kind of disappointing. It has been a very male-dominated profession, I guess, for lack of a better word, for the longest time. Marie Curie was a game changer in that. She was the first female to do a lot of things in physics and really paved the way for a lot of other people. And I think one of the reasons why she's the only, or one of the only females that get talked about in high school science is high school, we typically talk about a lot of old stuff, right? And we're building up to newer things. There weren't a lot of female scientists. It wasn't accepted at the time, way back when. So let's spend a minute talking about Marie Curie. Did you know that she is the first woman to win the Nobel Prize? She's the only woman to win the Nobel Prize 2 times, once in chemistry and once in physics. There have, throughout history, only been 3 women to win the Nobel Prize in physics out of, I believe, 209. Marie Curie being one of them, the first one. Donna Strickland, Canadian Donna Strickland, is the most recent one. I think that was 2018 or 2019 that Donna Strickland did that. So she's the only person ever to win 2 Nobel Prizes in 2 different disciplines, one in physics and one in chemistry. She's the first woman to be a professor at the University of Paris. She coined the term radioactivity. She founded the Curie Institute in Paris and Warsaw, which are now major medical centers. She discovered 2 elements, that's right, 2 elements, polonium and radium. And she discovered the link between radium and its treatment of cancer cells. So started that down the road. So pretty impressive life when you think about it, right? The first woman to do a lot of this stuff, the first person to do a ton of this stuff, the only person to do some of this stuff. I like it. That's excellent. Anyways, let's get back to the topic at hand. We took a little bit of a side road there, but an important one nonetheless. So factors affecting radioactivity. So people were interested. Marie Curie did a lot of work with this. Originally, people treated it like a chemical reaction. So you heat things up, chemical reaction goes quicker. You apply pressure, chemical reaction goes quicker. No, not decay reactions, not radioactivity. Heat it up, doesn't change a thing. You apply it to high pressure, doesn't change a thing, right? Nothing really changes it, not the same way chemistry would anyways. Turns out there are only 2 factors. That's right, only 2 factors that affect the radioactivity. So the amount or the mass of the sample that you've got in the first place, and then the half-life, or in other words, the type of radioisotope that you've got. And we're going to explore both of those in a second. Well, I mean, mass right now, literally a second. So the idea with this is, and I like to kind of think about it as flipping coins, right? You flip a coin, there's a 50-50 chance that it's going to be heads versus tails. Same thing with this, right? So we start with all heads. Let's say that heads is a decay and tails is no decay. Cool. All right. So you flip one coin. You might have 1 decay. And you also got to put a bit of a time limit on this one as well. So let's say that we can flip a coin every 5 seconds. And so every 5 seconds we flip coins. Well, if we were just flipping one coin, every 5 seconds we might have 1 head, so 1 decay. At most, right? There's like 1 coin. But if we had 1,000 coins, right? Every 5 seconds we're flipping 1,000 coins, then all of a sudden we're going to have every 5 seconds we're going to have about 500 decays, or about 500 heads coming out of that. If we had 1 billion every 5 seconds, we'd have 1 billion decays. So just the more you have, the more likely it is that you're going to have decays. Cool. The half-life. This is the time required for half of the atoms in a sample to decay. Sounds kind of weird. Each radioisotope actually has its very, very own unique half-life. And again, I like to think about this in terms of flipping a coin, right? So it takes a certain amount of time for different groups to flip coins, right? You go down to the kindergarten thing, it's going to take hours to get the class to each flip their coin once, right? Every kid gets a class, it's going to take them hours just to get that organized so they flip a coin. You can have like, you know, I lost my coin, stuff like that, all that different stuff to deal with. You take it to physics 30, you're like, okay, everybody, let's flip our coin, 1, 2, 3, go. Let's flip it again, 1, 2, 3, go. Let's flip it again, 1, 2, 3, go. It's going to be much, much, much smaller as we go through, and smaller amount of time in order for that to happen. Cool. So the time required for half of the atoms in a sample to decay. So let's think about this for a second. We've got something like thorium-234. The half-life, so time 1/2 for thorium, is 24 days. So if I started with a sample that was 100 thorium-244 on day 0, after 24 days, well, half of it would have decayed. Now I've only got half thorium-234, sorry, and half daughter material. Now I'd start with that half, and I'd say to myself, okay, well, after 48 days, that's another half-life. Your half is going to be cut in half again, or you're going to have a quarter of your original sample. After another one, I should attempt to draw this out here. After another one, so cut it into quarters. Now your quarter is going to be cut in half, or you're going to have an eighth, and so on, and so on, and so on. So the pattern that this makes for this, if we start with a percentage of sample, we start with 100% parent, and then after 24 days, we only had 50% parent, and then after 48, we have 25%, then 12.5 after 72, then 6.25, then 3 point whatever, and we see this pattern, right? This decay pattern that we've got right here. So percentage of sample, I should include this left, or in other words, our parent material that's left. See that exponential decay. Very, very nice. Very good. Short versus long half-lives. So if everything has its own half-life, right? Oxygen-19 has a half-life of 29 seconds. Uranium-235 has a half-life of 710 million years. Very, very different. I wonder which one of those is you would consider to be more radioactive. A short half-life or a long half-life? Which one of those do you think is more radioactive? Remember, radioactive is the emissions per second. So let's say we started with the same amount, 100 units of oxygen-19, and we had 100 nuclei or 100 units of uranium-235, right? 100 units. I don't know why I'm doing that. Different. Cool. So after 29 seconds, you would have 50 decays being given off. After, let's see, 29, after another 29, I'm not going to bother doing the math on that one, you would have 25 units of radiation being given off, right? So 50 units given off, and then 25. For uranium-235, let's think about that. So after 710 million years, you would have the same number of radioactive emissions. Which one of those is giving off more per second? Obviously, oxygen-29. So long story short, a short half-life means more radioactive. We're not going to do that quite yet. So let's jump in. There's an actual formula to deal with for this one, the equations for half-life. There's lots of n's in this, by the way. So n naught is the original amount of sample. N is the final amount of sample. Lowercase n is the number of half-lives that have passed by. T is the total time on the shelf in quotation marks, so the actual amount of time that has passed. And then what's not up here is T1 half is the half-life, so the amount of time it takes for half of that to decay. So things that we look at, we've got a ratio over here. Ratio means it has to be the same units. Could be years, could be days, could be seconds, could be who cares anything else, as long as the total time and the half-life have the same units. We're good to go. Same with this over here, actually. So I could have this in terms of percentage, as long as they're both in percentages. Actually, I put the 100 in the wrong spot. We could have this in terms of becquerel, as long as they're both in becquerels, the original amount and the final amount. So it could be in percent, could be in becquerels, could be in, what's some other common ones? I'm drawing a blank right now, but doesn't matter as long as the unit is the same. Cool. So a quick example here. Now, there are two different ways to deal with an example like this. You're going to kind of laugh when you see it, because we've done all this tricky physics through the whole thing. So two different ways to deal with this. We could either use logs, and if you've taken Math 30, absolutely, you can use logs. Or the alternative is guess and check. And that is what you can get away with for Physics 30, to be completely honest, because you don't need Math 30 to take Physics 30. Anyways, let's have a look. So you got a total time of 116 seconds. Cool. That's required for a radioisotope's activity to decay from 1,500 becquerels down to 93.75. So 1,500, that was my original amount of radiation, or radioactivity, and 93.75 times.5, that is my final amount of radioactivity. We want to determine the half-life. So let's check out those two formulas that we've got. We've got N is equal to N naught times 1/2 to the power of N. I told you there's a lot of N's, so keep those ones straight. And we've got N is equal to T over T 1/2. Cool, okay. So let's see. Our goal is to figure out the half-life. So this is my question. Let's see. I'm given this. I know my total time. I should probably figure out my number of half-lives. So I have to figure out number of half-lives. I know this. I know this. So here's a guess and check way to do it. I know, I'm just going to fill in some of the things. I know that my final amount is 93.75 becquerels, which is going to be equal to 1500 becquerels times 1/2 to the power of N. I just have to figure out what N is. So I'm going to go through. I'm going to do 1500. Oh, calculator didn't turn on. 1500 becquerels times 0.5, because that's the same thing as half, right? And I'm pretty sure it's not 1 half-life, so I'm just going to go 0.5 to the power of 3. 187.5, that's not quite enough, so I think I need more half-lives. So I'm going to go second function entry. So instead of to the power of 3, maybe I'll try to the power of 4. 93.75. So based on my guess and check, essentially what I figured out is that the only way that this will work out to make this equation true, if it's to the power of 4, therefore N must be equal to 4, right? Another way that you could do this kind of guess and check, I suppose, is we could do 1500 times 0.5 times 0.5 times 0.5, hit enter. Oh, that's not enough, times 0.5, 93.75. So how many 0.5s did we multiply by? 1, 2, 3, 4. 4.5s, same thing, N is equal to 4. Cool. From here, we just say N is equal to T over T 1/2. I'm looking for T 1/2, or my half-life. So let's see, it's going to be my total time divided by the number of half-lives. 116 seconds divided by 4. I believe that works out to be 29 seconds. And you could probably even identify that as oxygen, what was it? Oxygen 19, I think was the example from before. I better go back and have a quick look. Yes, oxygen 19, cool. Good stuff. So that's the guess and check method. Again, if you can solve for N using logarithms, that's absolutely no problem. If that is in your repertoire, go for it. No issues there. Otherwise, you know, nothing wrong with guess and check. It's actually a pretty good way to do a lot of things in life. So I believe, let's see, that's space to work, that's space to work. I believe that is it for our lesson today. A nice, fairly short one. Anyways, we will look at half-lives a little bit more as we go through the following lessons and some practical applications from half-lives. But that is it for now, Physics 30s. We'll talk to you again soon. Bye-bye.